Those Space People, a podcast series of casual cosmic conversations with people working on exciting space projects. Welcome to Thermal Lens, a special series focusing on thermal remote sensing, created by me, your host Rachana Mamidi, Agnieszka Sojinska, and Jennifer Susan Adams. Agnieszka is currently a research associate at the University of Leicester in the UK and has been working in the area of thermal remote sensing since 2017. Jennifer is a postdoctoral researcher at the University of Zurich in Switzerland and is currently focusing on measuring land surface temperature over forests. Agnieszka and Jennifer are also chairpersons of the Thermal Remote Sensing Special Interest Group of EARCEL, the European Association of Remote Sensing Laboratories. This group aims to bring together all the relevant stakeholders and provides a communication platform in the form of workshops, special sessions, seminars, and more. Agnieszka and I are hosting today's episode with Michael Perry from the University of Leicester. Mike is an expert in land surface temperature and was involved in the ESA missions LSTM, the Land Surface Temperature Monitoring Mission, and Sentinel-3's SLSTR, its Land Surface Temperature Radiometer instrument. Mike has a background in physics and did his PhD on new retrieval methods for LST and emissivity.
Hi Mike, it's great to have you with us today. So our subject today, the land surface temperature, has been quite controversial in the last months, and we are excited to talk to you about that.
Okay, so as the noob in this conversation, I have no clue what is the controversy you're talking about, so maybe you can throw some light on it.
So with the recent heat waves, we have seen a lot of maps published as illustration, and there were numbers like 45 degrees, and people seeing that were saying, hang on, there were only like 30 degrees that day. And this is because the maps showed the land surface temperature and not the air temperature.
Okay, so how exactly, like, what is the difference between these two and how is it calculated? And yeah, maybe you guys can give a quick overview on what's the difference and how it's calculated and why it caused this kind of an uproar.
Yeah, sure. So one of the big differences we're seeing here is what we're used to over decades and even centuries of people measuring temperature and what we're currently getting from the satellite. So if you think of temperature records, almost certainly what you're going to be thinking of is air temperature. If you listen to a weather report on the news, they'll say air temperature. And that's what people are talking about. And they say, hang on, it only got up to 30 something. And this is because the air temperature is what we feel. It's the most useful one around us when you're walking around. It's what's going to really impact your skin. It's going to make you feel hot or cold. And it's also the easiest one we had to measure before. You get a thermometer, you can measure it. It measures the air around it. But this is very, very difficult to measure from what we do in remote sensing. And this is where land surface temperature comes in. So land surface temperature is usually worked out from remote sensing. And what we mean by remote sensing is we're not going to be exactly where we're measuring. We're going to be some distance away and we want to know what the temperature is. So in the case of what we'll be talking about probably a bit today is satellite remote sensing. And here we're trying to use information we get at satellite to work out what the temperature of the Earth is. Now, we can't measure the air because the air is in this vertical column. So the temperature a few centimeters off the ground, or the temperature a meter off the ground, or the temperature a kilometer off the ground would all be different things. But what the satellite measures is the surface temperature. And this is where the land surface comes in. So this is the temperature of that skin layer, that top layer that the light, what we measure in the satellite, leaves from the surface. So it could be the top of a roof or the top of a tree or the top of blades of grass. The light that leaves those surfaces goes up to the satellite, and it's the temperature of those things we're measuring, not the air. Now, this leads into what Agnieszka was saying about why it's hotter. So these surfaces can get a lot hotter because they can store up heat, and often they have different properties. So say, for instance, tarmac. This is probably where people have an instinctual understanding of what goes on there. On a really hot day, there'll always be adverts around saying, don't let pets walk on hot pavements. Dogs can hurt their paws when they go on walks and stuff. And you may think, well, why? Well, this is because the tarmac heats up so much more. You've often got a very dark surface and it takes in all this energy, it heats up, it keeps that heat, and it can actually be a lot warmer than the air around it. So this is why you can have up to 10 or even more degrees difference in these temperatures. So when these maps that we were talking about before came out, these would be from satellite remote sensing. So they're measuring the surface. So they might look at a surface, it's 45, even in some extremes in areas like 55. The reason why these temperatures are so much higher than you might think from the air is because they're measuring the surface. They're not wrong, they're just measuring something a little bit different. And actually communicating that difference is very important and not done enough.
Okay, I'm gonna circle back a little bit to when you said it's actually light, that is light reflected off the ground, which is calculated in remote sensing. So, how do you derive the temperature value from this information?
Okay, well, there's several different ways, but fundamentally it all starts with that light. So there are different detectors that will be on different instruments, and they've got various different techniques to measure this light, but what it will come down to is measuring photon count. So this will be the amount of photons, which are little packets of light, that it measures in a particular wavelength. In this sense, we're not looking in the visible, we're looking in the thermal infrared, and that's how we tell temperature. So you'll then get at the top of the atmosphere this measurement of photons. Now you can turn this into radiance, which is like a measurement of the amount of light we're getting there. You can also convert it into something called brightness temperature, which would be like the effective temperature that radiance would have if you were measuring an object. But you are still stuck at the top of the atmosphere. So then you've got a number of different methodologies. There are tons of different retrieval algorithms out here that we're constantly working to update and refine. But you need to do one very big thing, and that's correct for the atmosphere. So as the photons have traveled from that surface all the way up to the satellite in space, there's a whole process of things happening to it. So you're going to have some of the energy will be lost of those photons, absorbed by the atmosphere, but the atmosphere also has a temperature, and some of that temperature will come from the atmosphere itself. So all these signals get mixed together and muddled up, coming from different parts, and you have to have an algorithm that tries to either work backwards through them and pick out the threads until you can get back to the surface, or there are ones that use statistics, so you know that this type of atmosphere, this type of location, you can assume it lost this much energy or gained this much energy. And you use one of these algorithms to then account for the atmospheric correction. You then also need to do a bit of surface correction, because the temperature at the surface will be emitted, but not 100%. So there's a term called emissivity, and this is the fraction of the temperature of that surface that is turned into light. So if you had an emissivity of 0.9, 90% of the temperature would be turned into thermal energy here. Whereas if you go down or up, a certain amount will be different. So you need to then work out what the property of that surface is, so you could work out what that amount of light translates to in terms of the temperature. And there are a number of different ways of that, and we're looking at loads of them in the group that I work in, and also there's a global effort to work with different sensors and different methodologies to retrieve land surface temperature from these readings.
You mentioned that there are a couple of different temperatures. You already said top of atmosphere, you said land surface temperature, you mentioned the difference, and then you mentioned also algorithms. So, how many algorithms and what algorithms are there? And you mentioned your group work in Leicester with them. So, what does the group do?
Okay, so there's probably a very large number of algorithms because a lot of groups make their own, but they could be broken down usually into a few categories. So I'll just group them up. So the first and most common would be a split window algorithm. And this has been popularized by a number of sensors that went on a number of NASA and ESA missions that had two thermal bands, so two windows in the thermal infrared that they looked at, that had a very useful property in that they had a different reaction to the atmosphere. So you were actually able to look at the two different bands and sort of work out by looking at the difference between them how much the atmosphere was affecting what was going on. So that's called a split window. And basically, how that works is you get millions of different atmospheres in models from data that we've got from a huge variety of sources. And you just run through millions and millions of these profiles and you band them together into coefficients so that you can have a lookup table. You could say, this is a tropical rainforest with this kind of water. So based on that, with these two channels, we think this is going on. So that's one method, very simply. It also does surface terms. Another method would be to try and do the surface and temperature together, so the emissivity and the temperature together. So there's methodologies for this that are typically called simultaneous surface and emissivity retrieval. So there's a few of those. So one of them would be an optimal estimation one. That's what we do in Leicester currently. So optimal estimation is fairly statistical in nature, but essentially the brief breakdown is you take a guess at what you think it is, and then you use that guess to work out what you should see at the satellite if your guess was right. And then you look at the difference between your guess and what you did see, and you keep updating your guess loads and loads of times until eventually your prediction of what the satellite should see matches what you do see, and that gives you some confidence that your estimation is right. There's also one that's done by NASA, and that's TESS. So that is looking at that works at the bottom of atmosphere. So they rely on a model to correct for the atmosphere, and then they do the surface estimation, that emissivity, using laboratory spectra, where they look at loads and loads of different materials that have been measured in a laboratory setting, and that allows them to create statistical relationships between what they see at the satellite in those bands and what they can estimate those surface conditions to be. There are also single channel ones, but they're generally a bit less accurate, and there's a move away from those as they were a bit basic.
So let's say you get the land surface temperature of, be it a forest or a city or an agricultural field or the ocean or whatever it is. And then what happens? What do we infer from this value?
So there's a number of things. So on its own, it can be useful, as there is a sort of relationship that we are used to using air temperature, but we don't have air temperature everywhere. So we can, through the power of global remote sensing, have surface temperature everywhere. Now, while the relationship isn't perfectly one-to-one, it's not like -5 degrees from the land surface temperature, you get air temperature. The rough relationship is still quite useful. So you can see patterns of hotter and colder. And while that sometimes isn't strictly accurate, it still gives you a sense of the temperature globally, which you don't usually have access to because air temperature is station-based and sporadic. So that on its own, for having an assessment of where temperature is distributed, where it's hotter, where it's colder, is useful. But also land surface temperature is fed into a lot of model data. So one of the more popularized ones, but this is perhaps a bit more controversial because sometimes people extrapolate a bit too far, is urban. So people want to understand urban heating. We know that in heat waves, events like this, people who live in urban areas are at much more risk, especially at night where those hot materials don't cool down. Particularly the elderly can succumb to heat-related maladies due to this. And that you can put land surface temperature in. But I would say that that is a field that is a bit more experimental because all those health relationships, it's important to remember they've been developed over decades and decades of air temperature. So it's not okay to just plug in surface temperature, but we're just working on those. There's a big one towards agriculture. So there's a term called evapotranspiration, which is often used to measure and understand the health and productivity of crops and things like that. And surface temperature, along with other parameters, is fed into models to look at that. And that's a very big one. So you can look at drought indicators with surface temperature as well. And something that's quite close to the group in Leicester, because we are the leaders on the ESA Climate Change Initiative for land surface temperature, is you can use the trends of surface temperature to look at the changing climate. And that's at a much coarser resolution, looking at the whole globe or particular regions. You can track the trends over in our case now, like 20 years plus of data, and you can have a look at how it's changing over the whole Earth. And there will be tons of other smaller applications where it is a niche where the land surface temperature provides you some input.
Okay, let me stop you for a second here. You say 20 years plus of data, but there are no sensors or very few sensors that can provide data for 20 years, and they're certainly not having a global coverage. So, what's happening there?
So the sensors that probably go back in terms of stable data records would go back to the AATSRs. So there's a series of sensors, AATSR 1, 2, and 3, which is double AATSR. These have got a good long temperature track. There's also the MODIS instruments, which go back to 1999, I think it's launching. And it sometimes makes me feel very old, but an instrument that was launched in 1999 does now provide us with 20 years of data, which is upsetting to me because I always think it was 10 years ago, no matter at what point I'm in. But one of the points that is a problem, and this probably relates to what you were pointing towards there, these are a number of different sensors. And one of the big challenges is stitching them together. Harmonization, we'd call it, because very few missions, with the exception of MODIS, have been continuously going for this length of time with no interruption. And especially when we look to go back even further. So there are sensors like the AVHRRs, which go back even before the 1999 one. But when we try to put different records together, you have to be very, very careful, because if you've got one sensor, it's not simply enough to get the two time series of this is how long AATSR ran and this is how long MODIS ran, and just, I don't know, average between them. They will have different effects. Each sensor will have its own biases, its own quirks. Its orbits will be at slightly different angles, observations, maybe even times of day. So a big effort, and this is one of the things we have been looking into in the ESA CCI project, is to try and harmonize these data so that we can have longer and longer time series that you actually have confidence in the results, because it is tricky to make sure that they match well.
So, in the end, if I'm a user who doesn't know much about land surface temperature, but I want to start, what do I need to know? What do I need to consider before choosing a data set, finding the right one?
I think that the first thing is you have to be quite clear in scoping your application. So if you're looking global climatic, then there are a number of sensors that you could look at that are at 1 kilometer, but they get you 1 or 2 observations a day at 1 kilometer. Is that sufficient for what you're doing? If it is, if 1 pixel being a 1 by 1 kilometer square twice a day of 20 years is what you're looking for, that's great. I'd point you towards I would, because I'm biased, point you towards the ESA CCI climate data. I think it's on the Copernicus data store. I'm sure we can provide links to that. But that would give you this global view. If you're interested in a particular area at coarse spatial resolution, so like 3 kilometer pixels, but you are really caring about seeing the temperature range during the whole day, I'd point you towards the geospatial satellites. So geostationary orbits are always looking at the same location. They are further away because they're like I think it's like 30,000 kilometers away. So they can only achieve resolutions of about 3 kilometers, depending on where you're looking. But they can observe at least every hour. So if you really care about how temperature changes through the day, but you don't care so much about the resolution, those would be great for you. If, however, you really care about the spatial resolution, as a lot of people who try to work in the urban areas do, then you need higher spatial resolution sensors. So things like Landsat, which look at 100 meters, Aster, which looked at about 90 meters. And there's, fortunately, which is quite exciting, a whole suite of new sensors coming out at this high resolution, ranging, I think it's about 50 to 100 meters in 3 sensors called LSTM, SBG, and Trishna, which involve LSTM is an ESA initiative, SBG is a NASA initiative, and Trishna is a joint French-Indian mission. And they're all going to be looking at much higher resolution, but they're new. so they won't have much data going back in time. The Landsat data record does go back to the 80s, but people often make the mistake of thinking this is one sensor. Landsat is actually many different sensors that all share the same name. So you have to be very careful stitching that together. And sadly, the Landsat ones, up until very recently, only had a single thermal channel, which meant that the retrievals from it were more difficult and you'd probably end up with larger errors. So I think that that's probably the scope that I'd give to somebody who's looking at there. Be very realistic with yourself about what your application is, because you might say, oh, I want to see everything at 100 meters, but do you actually need that? It'd be nice if everyone would choose to have beautiful imagery with the most high resolution, but if actually you're looking at how agricultural fields change throughout the day, it might be more than sufficient to say, well, this is a huge farming area, 3 kilometers is more than enough, and I can see that every hour. So I'd be quite realistic with myself about exactly what requirements you have. And that will guide you to the data set and probably make you much happier.
You've mentioned a bunch of data sources like Aster, Modis, Landsat, and a bunch of more upcoming missions. How to access these data sets, and are they free? Can we just download them online?
I believe, yes, free to all of them. The Aster record was paid for back in the past, but that's no longer the case. So I believe each agency will make these available to you. So you could go to NASA for MODIS and Aster. You could go to ESA for the Sentinel-3 and the AATSR. But, and I am biased on this, I think that you want the most processed and harmonized formats, the ones that actually share common properties with each other. So for a lot of the data, particularly the 1 kilometer data, which we've got a lot of different sensors, the Climate Change Initiative, the LST CCI, which has a website and links to something called the Copernicus Data Service, which has a huge amount of these data sets there. I would recommend those.
Now, let's say I'm someone who's interested to work with land surface temperature and then I download these data sets. How do I go about next? What kind of knowledge or skills or tools do I need to process this?
So we're hoping that this is something that interfaces at multiple different skill and expertise levels. So the files themselves are something called CF compliant. Now, we don't need to go into exactly what that is, but it means that most programs that will try to read the data, so I'm talking GIS programs, ArcGIS, NV, those kind of things, will, when they scan the data, find expected terms in there and know how to treat the data. For instance, latitude and longitude will be filed correctly within the file, so it knows what to look up and it should be able to take that out of the data quite quickly. So if you're somebody who's worked with a number of GIS programs, in theory, all the data should just work with those things. I know that you should be able to open them with a lot of different software packages. So a quick Google will take you to a Python script that does it. In fact, in the part of the CCI program, we ran a workshop, and I believe we got a public GitHub repository, which is the simplest thing ever. It's simply just a script that opens the files. So if you don't want to do anything, but you're comfortable enough in Python, but you don't want to learn all new programming, you can go on there and see how it opens, and it's very simple, and you can look at what's in the data. So that would probably be the easiest way through it. I think if you're also familiar with cloud computing, so the Google, I forget the name, is it Google Earth Engine? Yep, Google Earth Engine. They have a huge number of these data sets on there, and I think LST is on there as well. So if you're familiar with working on there, I believe there are some LST products. I don't know what the source is because Google harvests free data and all the data that I work with is free. So I don't know which one they will have taken it from. But there are other platforms, obviously, like the Amazon ones, and I believe there is also an ESA data hub, which they're creating and adding more tools to, where you can actually play with the data on the ESA platform. So my hope is that there's a range of options that should match a variety of different skill levels. But I guess that's for the users to feed back to us if there's a gap we're missing.
Again, we've already talked about agriculture and urban applications, but that's also not the only applications that surface temperature groups works with, right?
No. So, as I said before, climate is one that stands out on its own. It's getting a good quality climate data record, looking out there. There are also a number of applications that, well, I think you'll know more about this one than I would. So, in the like geology side of things, there's been things working on there. So I know that you can work to find different like heat events. So it's not just um, heat waves, the natural flow of things. There are certain signatures to other materials that stand out, or geothermal activity that stands out. One that is technically still within the LST, but it's often spoken about separately, is fire. So obviously, we're measuring temperature. We can see when there's heat events. It's not usually used in the LST sense for fire detection, as that usually uses different lower wavelength bands, but you can still see some of the burn damage and some of the impacts here. And we are hopeful that it's going to be used in some kind of forecasting. So various Met agencies that do forecasting based on satellite data being assimilated in, we are trying to convince them that now the LST is of sufficient quality that could even be fed into forecasting.
And then there's sea surface temperature and ice. They're so little known in the community.
Yes. So we kind of divvy them up into domains. So sea surface is probably the oldest heritage one because it was the first one of the temperatures that we measure from space that was thought to be essential for understanding climate change. So the sea was 70% of the planet. The temperature of the sea is something that usually is very predictable. There are cycles, there are flows. So measuring this and the change is critical to understanding how the planet is reacting to the change. So that is a very different regime, though. So as I said before, right back at the start, there's this feature of emissivity. So emissivity over the land is very variable because materials have such different properties. So an aluminium roof will emit very differently in terms of temperature to a blade of grass. Sea surface temperature, this is less of a problem because it's water. It may have different salt contents, it may have different, but when you zoom out to the 1 kilometer pixel level, it's all water. So they can neglect that and focus on other things. Ice then kicks in with its own range of problems. One of them, which is less of a physics problem towards temperature, is cloud detection. So knowing whether you're looking at cloud or ice is pretty difficult because if you use visible data, they're both white. And if you use thermal data, they're both cold. So actually working out whether you're looking at cloud or ice or snow even is pretty difficult in those regions. They offer their own different challenges.
This is one of the things that is still not very well solved in the thermal remote sensing, right? Cloud detection.
Absolutely. Cloud is a very big problem. So cloud impacts in many ways. So everyone's very familiar with the big, thick, white, fluffy clouds. And those are relatively easy to detect, at least in daytime. And especially they can be easy to detect at nighttime over warm areas because they stand out as these cold anomalies. But if you're in a cold region of Earth and it's nighttime, you're going to really struggle to work out if you're seeing cloud, whether it's just cold. There's also the fact that clouds don't just affect the bit that they cover up, they cast shadows. So if you can imagine that the sun is maybe at 45 degrees, it's going to cast a shadow that is not directly under the cloud. But if your satellite was looking straight down, it wouldn't see the cloud, but it would still see this area that is being shaded from the sun by the cloud. We need to work out how that affects things as well.
And this can be many kilometers away from the cloud, then, in the perspective of an image.
Absolutely. So it's very, very difficult. We're working on that actually at the moment, trying to use geometry basically to say we've detected a cloud here and the sun is at this point. So where will the shadow of this cloud be affecting the surface? But clouds are a big problem, and we end up with something called a clear sky bias, which is because we can only measure where there isn't cloud, we don't know how things are affected where there is cloud. So it's not a simple matter of just filling in and saying, oh, well, under the cloud, you can just drag the temperature out or something and fill it in or smooth it or interpolate it. We get this bias where we can only analyze situations where there isn't cloud, which is quite an interesting problem.
Wouldn't it help in this case when the thermal imagery is used in combination with visible imagery?
It does, especially during the daytime, but you can get thin cirrus clouds, which are exceptionally difficult to see in the visible imagery. They are effectively transparent, but due to the water vapor content they hold, they still affect the thermal quite strongly.
Would hyperspectral or any other kind of data sets help?
Absolutely, but then they come with their own problems. So you can circumnavigate this issue by using microwave. Microwave will merrily just go straight through the cloud, and you can measure temperature with microwave. This comes with two caveats. One, microwave is generally at coarser resolution because the way the detectors have to be built to get the microwave radiation, you generally would be looking at much coarser. So it's getting better, but the example I'd use is a 25 by 25 kilometer pixel for microwave, which, depending on your application, might not be as good. And then you end up with this small issue that microwaves actually are capable of penetrating into the ground. So technically, it's comparing apples and oranges because the thermal will be literally that top skin layer. It cannot come from anywhere below. Whereas depending on the surface, the microwave could be a little bit deeper down into the surface, which could radically change the temperature depending on what you're looking at. So microwave is really useful. And again, this is an area we're looking to further. There's actually a PhD student working with us now who's been looking into this, and she's advancing this, we hope. And it's a problem that we'd love to tackle, but there's no magic bullet, sadly. There are lots of other data sets we can compare to, but they all come with their own caveats.
Okay, now that you mentioned a colleague, what are the typical backgrounds of your colleagues in your surface temperature group? What kind of degrees are needed to get into the LST?
Our group will have a bias towards physics because we are a department that is technically part of the Department of Physics and Astronomy in our university. However, that being said, we recruit from a range of backgrounds. So we have people from geography who often come in. We've had a number of people from geography who tie into us, not specifically in the land surface temperature, but chemistry often ties in here as well. There are people who can come from a maths background coming in there who are interested in solving the retrieval problems. Some groups have dedicated retrieval scientists who come from a computing background, who from the computer science come in there. So what I would generally say is our broader group, if you zoom out from the land surface temperature, is Earth observation science. And that is a very interdisciplinary group. It spans basically any group that would be interested in this. So geography, maths, chemistry, physics. And broadly speaking, you're going to be, by the time you come into a PhD level, which is where a lot of the research in this really starts, also at masters, you'll be picking up the skills in different areas, but you'll get all the skills along the same route. I wouldn't say a particular route disadvantages you or gives you a boost in these ways. So if you're coming from a background in geography, you're going to be fine at doing all the rest, and the same with physics, you're going to be fine. You may have some areas that you had a stronger base in from your undergrad, but you're going to have to learn different areas anyway. So you have to have a broad interdisciplinary mindset to really get to grips with this. You can't really stay locked into your lane and say, I am a physicist, I will do it like a physicist, because you won't be able to do that for too long. And in the same way, like if you're coming at it from a pure maths background, you'll have to eventually go into something that's not pure maths. And I imagine the same is said for geography. You'll encounter something that's not within the traditional scope of a geography degree, but you just have to learn from those different things. It is a truly interdisciplinary subject, not just by virtue or something, but by necessity. It has to be. Otherwise, physicists would have to reinvent the wheel on stuff that geography's been doing for hundreds of years, and it wouldn't work.
How about you? What brought you to work with the land surface temperature?
So I became interested in Earth observation in general during my undergraduate degree. So as I was doing a physics degree, I did a module with my future PhD supervisor. And I was really interested by the challenge, but also I thought it was really cool that we were able to use this data that was just photons hitting a detector somewhere in space and turn it into real physical meaning that we could try and work out that, oh no, this relates to that thing that you can go and put your hand on and it's real and it's there. And using the maths that we got there was really interesting. So when my undergraduate and master's finished, I applied for a PhD with this group. Unfortunately, I was able to get into it there. But I didn't start my undergrad with any of that. I started my physics degree convinced that I was going to go into, like, I don't know, robotics or rovers on Mars or something. And I veered quite hard when I discovered remote sensing and thought that was really fun.
We were already speaking about all the different sensors appearing, and you mentioned three different mission coming, and there are also a couple of commercial missions coming to put up constellations. So there is a lot of change in the field, but what do you think should still happen, or what would you like still to change or evolve in the field of thermal remote sensing?
I think that's a really good one, but I think it's as exciting a time as it is going forward with all these new missions. I think that actually establishing kind of like a science-led baseline that can help these commercial missions is crucial, because I think that we don't need every mission to do everything. And I think that these big missions that have happened historically, where you have really big, high quality sensors, have been the driver going forward. But as you said, there's a huge explosion in the commercial market. And I think that from a science perspective, we've really got an obligation to make sure that high quality data sets spanning a range of different spatial resolutions, temporal resolutions, and at high quality are made available so that these commercial missions can use them as a baseline to kind of calibrate and improve against, so that then they can focus on specific issues. I also think that working forward, I don't know how feasible this is. I'd love to see a high resolution microwave. I think that would be really fun to see. And like, how does that compare to the thermal that we've been seeing at the high resolution? But I think that, yeah, the commercial is not a flash in the pan. It's going to get more and more, as you said, these constellations going with, well, instead of spending huge amounts of money on a single incredibly high quality sensor, can we do 5, 6, 10 smaller satellites and constellation and use the fact that we've got a large number of repeats and observations to kind of average our way into high quality data that's more flexible? I think that's a really exciting push forward. So I think the thing I'd really like is to see a lot of communication between those two sides, so that the science doesn't see it as competition or anything, because they're doing different things, and provides its data and expertise to help the commercial go forward and deliver as high quality as possible. Because if the commercial entities are going to put money behind it and produce a lot of data, then that can only advantage the community as long as we can get some access to it.
I love that you're almost repeating what I tend to say within the special interest group. This is the time to cooperate and stop looking at being competition to each other.
Yeah, absolutely. Like, there's so much experience in the thermal remote sensing on LST from the science background. And it's from this very high quality science background. And it's very easy to look at what's being done as the commercial offerings and say, well, they're not at the same quality. And sometimes that's like almost said as a dismissal, like, well, why would you do it then? But they're answering very different problems. Like, if you're getting a constellation that's looking at like 10-meter thermal imagery over a city, you're not stitching that together for a climate data record. So they have very different ideas about what's going on, very different use cases, very different scenarios. And I think that science should be the science community should be trying to make sure that those are done as high quality as possible, rather than seeing it as any kind of competition or anything like this, because it's not. And at the end of the day, if the community helps calibrate these things, it's very common to see data exchange agreements. And if you see scientific projects or collaborations that say like, oh, we'll validate or calibrate this data, odds are you'll get access to it as well, even though it's commercial, and that can help research.
That's a lot of insights into land surface temperature. I mean, at least coming from an engineering background, you don't really think about what happens to the data after it's beamed down from the satellite to the ground. And I guess all the fun, begins then. That's when all the fun begins.
Yeah, and then it picks up again once you get really deep into the applications. One of the things that I like is when we go to like try to integrate more with users, and you'll talk to people and you'll see that they needed your data and you'd never even thought of this application. So I'm probably going to misquote this one, but there was a poster and some person from an ecological background who had used high resolution thermal imagery to like start mapping the migrations of animals and things. And I was there going, well, you can't do that. Surely we're looking at 100-meter squared, like you're tracking flamingos, I think it was. And like, no, you can tell the difference because like they eat the vegetation, or there's a huge herd or flock and it moves. And they sat there and gone, no, you can do this. And they've been able to track it back and do something that from a starting at the satellite perspective, it would never have been on my list of things that I would have thought you could do with this data. So I think it's really important to make sure that you let people know it's there because there'll be somebody who'll sit there and go, I could do something with that the people who work day to day making it would never stand a chance of thinking of.
I guess I've also heard someone mention at some point that you can also estimate the output, the milk production of a herd of cows based on how much grass they eat, the remote sensing data. So I guess there's probably imagination is probably the only limit.
Yeah, and with so much more data coming out, there's going to be a lot of like statistical, like the classic is like correlation isn't causation, but there's a huge number of statistical methods where you can say like, well, you can kind of track these things, and if they go in tandem together and you can track one of them, it gives you some insight into the other. And I think we're going to see a lot of tentative studies on that. Some will work, some won't, but I think it's important that we let the community try.
This is great. So we have covered so many different subjects and aspects here within the LST. And there will be probably more and more questions appearing from the community hearing this podcast. There will be a place for a discussion on the website when we publish the podcast. And if you have any questions in the audience, please post them and we'll try to answer them as much as possible.
Great. Thanks for the fun episode, Mike.
Thank you for having me. It's been great.